Hi, in this video we are going to demonstrate end-to-end anomaly detection model from feature engineering to model development and deployment using the Hopsworks platform. We will demo this using Python APIs and Jupyter notebooks, but I just want to point out that in Hopsworks we're also supporting Java, Scala APIs with other popular IDEs like IntelliJ. Alright, so let's open a Jupyter notebook and start with the feature engineering. So this is a typical DataOps. First we will define our feature engineering logics. Then we are going to access our raw data sources in real life. It could be data warehouse or some message bus where your raw events will arrive. Then we will apply and this feature engineering code logic and get a data frame that contains your engineered features. And then now we are ready to register this as a feature group to the Hopsworks Feature Store. So to do this, we are going to connect to Hopsworks Feature Store, get feature store handle. Then before writing it, we probably want to do some checks here. And then, for example, you may want to make sure that the arrived value falls in a certain range. For example, your customers knows your customer's age is a certain range. You might make sure that, for example, transacted amount should be a negative value, or maybe data should not be older than 2018. For this, you can use Hopsworks rules that comes with the predefined rules. You just have to define an expectation and register it, and later you will use to attach to the feature group during the creation. To do this, we just call create feature group method on the feature store handle, where we provide a name, version, primary, and partition keys. Whether you want to enable time travel format and you want to have for a low latency serving. And since we know this model will be used for low latency serving, then we want to enable the online feature store. And then expectation, we define here a strict, which means that if the value falls out of the expectation, then it will not insert to the or write to the feature store. Or you can define as well as a warning. So in this case, it will write to the feature group, but it will give you a warning. And we can also define if we want to compute statistics. This is highly useful if you want to, for example, monitor data or a concept drift over time. And once we create this feature group metadata object, then we can save it using calling a save method and providing a data frame. This will materialize this data frame as a feature group with associated metadata. Once it materialized, you can preview from the UI. Let's go to the feature groups, to this transaction feature group. You see here we can overview what are the feature types, which one are the primary partition keys. We can feature statistics, basically basic statistics, all the features we have it. We can also use the activity where you can, when it was created, how many features or how many rows were inserted. In this case, we see that 400,000 rows were inserted and no rows were updated or deleted. And we also can preview the data. As you can see, this will basically give you a nice, easy way to explore a feature group. So next, what we want to do, we want to create another feature group, which is graph embedding features. Graph embedding feature, where we want to take a large transactional graph and compress to the lower dimensional latent vector that will be used later on for our anomaly detection model. But for this, we want to develop another model, graph embeddings model, that will basically output our graph embeddings. Now what I will do, I will just get the feature groups which we registered, and I will create a nodes and edge training datasets. And then I will use this and then create a training dataset. In this case, the concept is the same here. In this case, we just call a create training data set and provide name, version, the data format. I'm going to provide a CSV file because later on I would use a Stellar graph, and Stellar graph uses as a CSV to read this data. And then I will compute the statistics as well. It's also very useful if you want to compare how the training data set diverged from the features that was created. So you can also monitor and debug if you have some data or a concept drift. Yeah, and then training data set also you can preview from the user interface, and basically it will be all the it's the same. You can see which types it has, if there is any statistics, etc. Now we are in a stage which we want to develop our embeddings model. But the first stage is in development model. We want to do find the best hyperparameters. For this, we are going to use Maggie. Maggie, you can define your search space. Then what you need to do, you will have to put your model logic in the wrapper function. Good thing about this one, you can develop this model logic in your local environment, let's say in your laptop, and you just don't need to refactor anything. You just put that logic in the wrapper function here, which will take just which hyperparameters you want to tune, and then Maggie then implicitly will take care to do a hyperparameter search in completely different environment. So it's useful, so you don't need to change any code. And then depending on what parameters and what search engine you used, it will output the best hyperparameters. Then once we have a best hyperparameters, we can read this and then do a model training. So the same here, we want to put a model logic in the experiment function, and depending what distribution strategy we will use, and we will launch an experiment. And this will register a model into the Hopsworks model repository. During the experiment, you can follow how your experiments perform. Here we performed the training, and we see that this was a hyperparameter tuning. This was how much different hyperparameters, which metric it reported. So this particular hyperparameters are the best metric. So we use this walk length 2, walk number 3, and the embedding size 16. And then we can also see how the training has performed, and that was the latest the metric or accuracy we use for this model. Now we have a model, and then we will use this model and retrieve from Hopsworks model registry to compute the graph embeddings features. Again, we retrieve the latest, the best model, and predict graph embeddings, and the register as feature group. And again, here we provide name, version, and primary key. And we enable time travel, we enable online, because we want to use this for the live monitoring system in a low latency serving. And they issue the same method, which will register our graph embeddings features into the Hopsworks Feature Store. Now, since we use the Rapids to deploy the Hopsworks, and we have a library Queuegraph, and Queuegraph is basically a graph algorithm on steroids. It utilizes GPUs to compute some graph features, and it is highly important performance. So I will use a couple of graph algorithms like a PageRank, so between us, the weakly connected components, compute them and assemble as a feature data frame and register it as a Queuegraph feature group. So we can use this in combination to our embeddings model to develop embeddings features to develop an anomaly detection model. In reality, you will have much more features. For example, you will have daily aggregates, hourly aggregates, and demography features. But for the simplicity and demo purposes, we used only graph features here. And then we are ready to move to the next level and develop our anomaly detection model. What I need to do now, I need to retrieve all the features I want. So I want node embedding features. I want Queuegraph features, which I use to compute a couple of features using different graph algorithms. And I will also use alert nodes to put labels. So first, in this model, since it's a semi-supervised model, I want to create a training dataset that does not contain any samples that have been previously reported to be involved in suspicious activity. So I want to learn what's the normal behavior. So I will select desired features using a query object, and then use this query object to register training dataset. And I will note here that since I used the Hopsworks query object, this will remember the order of the features as well as which feature groups used to construct this training dataset. So that during the online serving, Feature Store will know which updated features to send for the predicting if there is a new arriving data. So that will be basically used to perform a low latency model serving. And here is the same, but in this case, I will create a separate that contains samples which are suspected in suspicious activity. This will not be used during training, but this will be used for evaluation, model evaluation, and the model validation. All right, now we have all the ingredients to develop our anomaly detection model. I will again use a MAGI to find the best hyperparameters. So for this particular model, it's a GAN model, and as I mentioned in the presentation, GAN is notorious to be hard to train because it's very hard to find best hyperparameters, and a good hyperparameter search engine and a good infrastructure will give you this advantage. So it's a number of GPUs basically will be linearly related how fast you can find your best hyperparameters. So we put all our logic in experiments, the wrapper function, and define a search space. You can see here for GANs how search space is very large, and you need a good infrastructure and a good hyperparameter search engine to quickly find the best hyperparameters for your anomaly detection model. And then perform experiment. Again, you can follow the experiment here, and then see, and if you have a TensorBoard enabled, and to see which parameter, which metrics it reported. As the next stage, again here we will retrieve the best hyperparameters and perform a training. So depending on how many GPUs you have, how many DGX servers you have, you might want to, if you have one GPU, you can use the one device strategy. But if you have single server with 8 GPUs, it's a mirror strategy, or you can, if you have multiple servers, multiple GPUs, then it's a distributed mirror strategy. And then it will be very low, minimal refactoring here. Basically, it provides the oblivious function, so you can use the same code used in your environment, and can use the minimal refactoring. You can perform your distributed training, and then we are going to register this as a Hopsworks model registry, and then we will use this model to perform a low latency serving. Now, to do this, we are going to create a model serving using a Triton inference server. First, go to the model serving. I already defined, but this is so here basically this is also possible to do with the API call, but for demo purposes, I'm gonna show you how to create using Hopsworks user interface. You define the name, which model. You can drop down menu which models is available. We use the GAN, which version. We have only one version here, and since we want to use Triton, we say that if we have a Triton inference service available, we say that we want this is the endpoint will be used in Triton to get our predictions. Once we have this enabled, then we can go to the model server, basically start a Triton inference server, then get a feature to get a training dataset metadata. Training dataset metadata at this point knows which features you want to retrieve and how to assemble the serving vector. So it knows the order of the features. So the only thing it needs, we just need to know primary keys. So let's say I just defined the predefined list of primary keys, but in real case, it will be some application, let's say your transaction systems that your transaction happens and the primary keys will arrive, and then these primary keys will be used to retrieve a serving vector. So we just say get serving vector. This will retrieve the latest available data for these primary keys in the feature store, and used to send this REST API to send to the Triton inference server, and then since we deployed our anomaly detection model, it will retrieve scores. And then depending what was the logic of your scores, where was the threshold, then you can put which code was anomalous, and for example, higher values will be related to suspicious activity, and then lower ones will be more classified as normal, and then this will be sent to the investigators to further investigate that this particular transactions have some suspicious behavior. Now I have a couple of minutes to show also that since we deployed Hopsworks now with Rapids, we can use some dashboarding. For example, if you get some predictions in your investigators, you can define here I'm defining a notebook there where I will read transactions that have been classified as suspicious with the anomaly detection model, and then create a dashboard to further investigate it. And this dashboard can be used as well as investigators to dive further into and investigate this behavior.